especially with antennas. The discussion will be very basic with relevant information relating to radiation, the product of antennas. Most of the time will only involve simple antennas. However, I will have a short section with respect to antenna arrays at the end. So, let's get started. All right, so I'm zapping you. Does anybody feel that? All right, well, you're being radiated. But you're being radiated by everybody's cell phone in this room as well. And you're being radiated by all the electronics in the building. Okay? That's just the result of currents flowing and electrical wires and pipes and things like that. All right? We're totally inundated by radiation. Well, what's different about antennas is that we create radiation on purpose with antennas. The other ones are not done on purpose. Okay? This slide shows a few antenna types, which I'll discuss at some point. But the question is, what do we use antennas for? We use them primarily for communication. And that implies that there's at least two antennas in any system. One's a transmitter and one's a receiver. Of these showing up here, only the microwave oven is not transmitting and receiving. The broadcast tower only transmits. The other antennas there are used for both transmitting and receiving. The thing that's so amazing about antennas is that the transmitter and the receiver that we're talking about don't have to be connected together. Like in a radio system or a telephone, or rather than as a radio, telephone or telegraph, they were always connected together by a wire, no matter how far apart they were. But with antennas now, there's no connection between the two, so they can be put anywhere. And as they are today, you can have one on Earth and another one communicating with a satellite millions of miles off in space. So the basics here, let's say, what is an antenna? Well, an antenna is a device that transforms electrical energy into electromagnetic energy. Now that's a big fancy word, but basically it means radiation. To describe this effect, think of a metal rod that has some current on it, and then radiation comes away from that just because of the current. An antenna also works in the reverse direction. Just as important, antennas are sensitive to radiation. So if we have an antenna and we have radiation coming into that antenna, it will create current on that antenna. So it's a complete cycle. You can have it as a transmitter or a receiver to have a system like that. Now let's make a simple antenna. We can just start out with a two-wire line. It goes from some sort of source of energy, a signal, up to some sort of load that's insignificant here. But we take these two wires and we bend them like this, and now the current that was flowing on those wires is all flowing in the same direction. So that's accumulating and creating quite a bit of radiation now. Previously in the two wires, the currents was flowing in opposite directions that tended to cancel out. So there wasn't that much radiation when the wires are close together. Here, now we're creating a lot of energy, radiation energy. Now current implies the motion of electrical charges. All right, now they can't flow indefinitely in one direction. And it turns out that an antenna is actually a resonant device, just like elements in music instruments, like a string in a guitar or piano or a violin. The length of the string determines what the frequency is for the vibration of that string. The same thing is true in an antenna. If you want to change the frequency of a string in music, you change the length of it. And that's what we do with an antenna. If we have to adapt from one frequency to another, we set the length of the antenna based on that. Let's talk a little bit about, well, all right, I just missed a few clicks here, but that becomes what's called a dipole with the two sides to it. Sort of, there's two basic antennas, a dipole and a monopole, and everything else is built out of one of those two. Nothing more complicated than that. But we'll show different antennas that have different radiation patterns. Okay, so we get an oscillation back and forth on this resonant dipole, and we have to determine what the length is, and that's based on what frequency we're going to be using. So I want to first define a few terms with respect to radiation, because radiation and antennas go hand in hand. Okay? Radiation is an oscillating electric wave through space at a frequency where it has an oscillation rate based on whatever the frequency is. Just as an example, the frequency in your home, the power lines in your home, are oscillating at 60 cycles a second. Typically, in communications like this, they're operating at millions of cycles per second, tens of millions of cycles. I'll show you some examples of that. And that establishes the wavelength. And this, with this wave, the wavelength, as you can read it here, is determined by how fast something's going, the wave, which is going at the speed of light. And within one time and one period there, that's how you define a wavelength. And with respect to an antenna, typically a resonant antenna is going to be based on a half of a wavelength. So one of those dipoles that I was showing you before would be a half a wavelength long. So that's how size gets related to frequency, and frequency is related to the application that you're actually using it for. Now this is all done within the electromagnetic spectrum. And we see it's from 0 to infinity here. All these different types of things are all operating with the same electromagnetic spectrum that I'm talking about with antennas. Now, one thing that's particularly interesting here is the one section where you have visible light here right in the middle. It's just electromagnetic. All this light is electromagnetic radiation. We just don't think of it that way. And our eyes are sensitive to that electromagnetic radiation, so we see light, okay? Now the area that I'll be focusing on is just the lower end of this, where we've got all these bands of frequencies that we're pretty much familiar with just in normal life. AM, FM, radio, TV, cell phones, and on up to radar. And you see then in the next line, the frequency would go from 1 megahertz, that's 1 million cycles per second, on up to 10,000 megahertz for radar. And the wavelength is inverse related to the wavelength, or to the wavelength and the frequency are inverse related. So for the 1 megahertz here, that antenna would be, well, that's a wavelength, so a half wavelength would be 150 meters long, typically. And there are lots of antennas that size, but we're not usually using those frequencies. But you see, as you go on up here to the radar, and that's in an area where I was working, this higher end stuff, the wavelength is down to 1 inch. So we could actually building parts of antennas that are on the order of half wavelength. Now there's another factor characteristic of radiation that's particularly important that most people don't have any idea about at all. And that's polarization. So I want to talk a little bit about that. All right. So if we consider two antennas that are in a system, the one on the left, we'll call it the transmitter, a dipole there, and then a receiver over on the right-hand side. So that's just what I'm arbitrarily set up. These two are in the same orientation. So I'm going to use a couple sticks here just to show. If we call that one horizontal and the other one over here is horizontal, that's going to be the best connection of the radiation between the two. All right? And that's called copolarization when they're in the same plane. It doesn't mean it has to be horizontal. They could be both vertical like this or anything else, but they should be in the same plane. When one of the two, either one, it doesn't matter, gets cross-polarized to the first one, then your connection between the two, the transmission level is going to go down. Okay, and that's important. And cross-polarization always ends up hurting. Now, as far as, okay, this chart shows with the copolarization, which is at 0 degrees, where the two things are at the same plane, there's no additional loss between the two. It's whatever it is based on length and things like that. But as the angle, as the angle changes and goes out to 90 degrees, you get this worst case, and the transmission loss goes way, way down. Okay, so you don't want that to happen. So what I put at the bottom is when you have a problem with your cell phone and you're having a problem getting good reception, a good thing to do is rotate it around, because it may be that you just cross-polarized with the cell tower. I don't know what the cell tower is particularly, because I don't know what the polarization inside the cell phone is. But I know that you can change it and get different levels of signal through it, so it's worth dealing with. I do that myself all the time. But there is a way to round this, and it's called circular polarization. So what happens here is if we take one of the two antennas in the system, whether it's transmitter or receiver, back and forth, it doesn't matter, but you design an array with two different polarizations in the array and the other one, then no matter what this orientation is, it's always going to have some connection with one of these two in the array. Okay? Now the loss in this factor is a half of your power level, but it's all the time regardless of what this angle is. Okay, so that's very easy to give up a half of the power level, but never have to worry about the orientation. This is a picture of radiation coming off of a cross-polarized or circularly polarized antenna underneath it, coming up into the sky, and that type of polarization is used all the time for vehicles and aircraft and things where they're always changing their position with respect to connecting to satellites in the sky. So it's very, very commonly used. I doubt whether it's used in a cell phone though, because it takes more antenna space and it starts taking up more 3D space in there as well. So how do we see radiation? Well, here we have a picture of a flashlight with energy coming out, light energy, which is electromagnetic energy, although we can see it. It's coming out into a particular volume, and that's what we're particularly interested in. If I change it a little bit, I can change the type of shape of that radiation. And when it gets narrow like that, that's when they're more likely to call it a beam. Well, I take a flashlight like this, okay, and it's got, this is the broad kind of thing, and I can change it by focusing it down like that. You see how much more concentrated it is. The same amount of power that was in this broad beam is now all focused in one spot. And I'm only doing that for one purpose, and that's to define the term we use called gain in an antenna. The gain is what the concentration level is at the peak point of the beam that you're trying to create relative to if it was like a candle in a room where it's radiating out around in a full spherical shape. The same amount of energy put into a concentration, that would be the gain. So I will have examples where I talk about the gain of this antenna is 15 or 200 or whatever. So I just wanted you to have an idea of where that term's used. Antenna design is all about controlling the radiation patterns. You have a need to have radiation in a particular direction, whether it's a broad radiation or a very narrow pointing radiation. Like when you use dishes, you create very narrow beams and you can get from building to building in a downtown area or something to a spacecraft. Now here I want to describe the technique that we use in simulators to get an idea of what the radiation looks like. It's called a polar pattern. And polar because it's a three-dimensional pattern that shows the amount of power in this radiating beam. Okay? It's this picture here. In this case, it looks like a tire around a dipole, a horizontal dipole. So that's where the radiation is coming out normal to the dipole. It's not along the lines of the dipole. There's no energy going along the lines of the dipole. And it's very strong out perpendicular to it, and it has some width to it, and you see as it gets, the different colors show the strength level as it gets down into the little holes. Well, I should back up on this description. This red circle represents a horizontal plane that I'm cutting through this polar pattern. And then we can see on a two-dimensional plot, the figure 8 patterns over here are showing what the gain is all along that horizontal cut through that pattern. And if I look in this way around, it's like a tire, you would immediately see that that relates to the blue line over on the horizontal pattern. It shows that it's equal, omnidirectional all the way around. It radiates equal amount all the way around it. So let's take this very simple dipole. This is what was developed back in the days to prove that radiation was really beginning to be understood as a dipole. So here I have a simple dipole, and I have the radiation pattern below it that I've already talked about, but I want to add one other thing about it, is that I have what's called a front-to-back ratio of 1:1. That means if I had energy radiating out of that dipole, it would have amount going in that direction and an amount coming in this direction based on this figure 8 pattern in both directions. But I don't want that because I want an antenna that only shoots it in one direction. So this type of antenna, oops, wrong one, there we go. You can put a couple metal rods in proper spacing and placing with respect to the dipole. You don't have to do anything more to the dipole, but it will create a new radiation pattern, as I see there. And the front to back ratio now is 10:1. So that's pretty good, and that might be good enough for whatever you want done with this.